I hope you're not too hungry because I got to tell you, I just had, a buddy of ours has a smoker, loves to play with it, cooks all sorts of stuff in it, cooked up a really amazing brisket for us. And then I kind of mixed it up with some mac and cheese, and it has put me in a really good, happy place. So hope that didn't distract you too much, but I just had to share that with you. One of the best things I've had in a while. So we just finished up continuity at a point, and we investigated it graphically. Today we're going to continue on the same broad theme, but we're going to investigate it algebraically. My personal opinion is I think this is a lot harder than doing it graphically. And in a general sense, when anytime I analyze something graphically and then I analyze it algebraically, I usually find it harder, more challenging algebraically, at least until I, figure out how to ride the bike, so to speak. But so we're sticking with the same definitions here of continuity. Our not so rigorous definition down here says that as long as we can trace the graph without picking up our pencil, we're good to go. But our more rigorous definition says, hey, we've got to prove that all three of these are true, and all three of them. It's not good enough to have 1 out of 3 or 2 out of 3, but we've got to prove that all three of them are true in order to say that the function is continuous at that point. So we're going to dive right in. And one of the themes that you're going to see here today is that all of the functions that we're working with are piecewise functions, okay? And in fact, let me back up just a second because we're going to see a lot of trig functions in here today. And so just as a rule of thumb, so let's say, I'm trying to do the cosine of pi or the cosine of 2 pi or the cosine of 0. Okay, so let's think about what your cosine function looks like. All right, so if you have y equals the cosine of x, I like to use my graph of cosine to help me remember a lot of the key values. So right here, you've got 0. We'll put it up here. We've got 0. Here's pi over 2 if you want to mark that. Here's your pi if you want to mark that. Here's your 3 pi over 2. Trying to write so small, I don't know if it's going to pick up. And here's your 2 pi, which is up here. And if you remember, the maximum height is 1 and the minimum height is -1. So what happens is when we put a point right here, what we're really saying is that the cosine of 0 is equal to 1. Or if I put a point right here, what we're really saying there graphically is that the cosine of pi over 2 equals 0. If I put a point right here, we're saying the cosine of pi equals -1. Then we're saying the cosine of 3 pi over 2 is equal to 0. We're saying the cosine of 2 pi is equal to 1. In a similar fashion, let's just do a real quick review on that sine curve, because I don't want this to be the thing that trips us up if anything does trip us up today. I don't think it will, but if it does, I don't want this to be it. Okay, here's your sine curve. If I stop right here, I'm at pi. And then I'm going to continue. If I stop right here, I'm at 3 pi over 2. And if I keep coming, I've completed a cycle at 2 pi. So we've got 0. Here's our pi over 2. And maybe we just need to get out a sheet of paper and just practice drawing this a few times and just refreshing our memory. So what is this useful for? What do I use this graph for? So again, this point right here is telling us that the sine of 0 is equal to 0. This point right here is telling us that the sine of pi over 2 is equal to 1. Now, I think in yesterday we looked at, what's the sine of 30 degrees, also known as pi over 6, and how that's equal to 1/2. I think so. The angles were 30, 45, and 60. Those are some really special angles. The ones I'm focusing on right now are, the 0, the pi over 2, the pi, the 3 pi over 2, and the 2 pi. Those are what we call your quadrantal angles. They're the ones that separate quadrant 1 from 2 and so on. This point right here is telling us that the sine of pi is equal to 0, and et cetera, et cetera. So the sine of 3 pi over 2, make sure that's a 2, is equal to -1, and the sine of 2 pi is equal to 2 pi. Okay, so we've got that under our belt. So we've got this really crazy piecewise function, and you'll notice this function right here, x plus 2 quantity squared, has a domain of x is less than or equal to 0. And then we've got this second function right here with a domain of x greater than 0. And we want to prove whether f is continuous at x equals 0 or not. So the first thing we want to do is we want to prove that the general limit exists. And the only way we could prove that that exists is by first finding the limit from the left. Then we got to find the limit from the right and prove that they are equal to each other. So here's what this is going to look like mathematically here. And like I said, this is a big challenge for us today. This is going to be a good one. The limit as x approaches 0 from the left of f of x is going to be the limit as x approaches 0 from the left of the function x plus 2 squared. Then I'm going to do my direct substitution. I'm going to substitute the 0 for x. And once I do that, I'm going to get 2 squared, which is equal to 4. Let's see if I can pick out a new color here. Let's try this. Did that save? That didn't save. All right, let's try it here. Okay, now let's say we want to do the limit as x approaches 0 from the right-hand side of f of x, which in this particular case is going to be the limit as x approaches 0 from the right, and I'm using the function 4 divided by the sine of x plus pi. So it's still an x. I haven't done any direct substituting yet. Okay, now I'm going to substitute the 0, and it's going to be 4 divided by the sine of, now in your head, you're thinking, well, 0 plus pi is just pi. Okay, cool. And then you're wondering, oh gosh, what is the sine of pi? What is the sine of pi? Again, if you want to just do a quick little sketch, say doop-de-doop-de-doo. Okay, here's your pi, right? So that's 0. Well, 4 divided by 0 does not exist, right? So what have we proven here at this point? We just did the one-sided limits. They're not equal to each other. Therefore, the general limit does not exist. Okay, that's our little conclusion here. We'll say, therefore, the general limit as x approaches 0, of f of x does not exist. And therefore, f is not continuous at x equals 0. Okay. Now let's just assume for a second that, somehow I did get a 4 right here. And then we go, okay, the general limit does exist. It's equal to 4. Then you'd have to find f of 4. And what you do then in that case is you look for the equal sign. Okay. Do you see the equal sign right here? So the equal sign tells you that this is the active function. And basically, you would just substitute a 0 there, you'd get a 4 again, and then you'd have a continuous function because everything on your checklist was equal to each other. Let's go try another one. And so as you work these out and you do your one-sided limits and try to prove that the general limit exists, try to follow a similar format to what I'm trying to model here. So the first thing I want to do is the limit as x approaches pi from the left. So the limit as x approaches pi from the left of g of x is the limit as x approaches pi from the left. In this case, so I always say when I spell less than, it starts with an L, right? And of course, if I spell the word left, it starts with an L. So those two always go hand in hand. That's how I remember it. So left means I look for the less than sign. So I'm going to use this function right here. So we've got the cosine of x divided by 4. Now I'm going to substitute my pi. If I forgot what that looks like, I'm just going to draw a little curve here. Here's the pi, so that's a -1 divided by 4. Let's see if we get the same thing for the limit from the right-hand side. So let's do the limit as x approaches pi from the right of g of x, which in this particular case is going to be the limit as x approaches pi from the right. And now I'm looking at the greater than sign, and I'm going to use this function. So we've got 4 times the cosine of x minus pi. And if I substitute a pi, I'm going to do right here, I'm going to do pi minus pi, which makes 0. Cosine of 0 is this point right up here, so that's a 1. And 4 times this 1 makes 4. Oh my garage, these are not equal. How about that? So what we're going to conclude right off is we're going to say, okay, therefore, the general limit as x approaches pi does not exist. And therefore, g of x is not, we repeat, not continuous at x equals pi. So, shucks, we've struck out twice here so far. Let's see if we can try to rally on this next one. Maybe we can keep your fingers crossed. Maybe we could actually be continuous for once. All right, so just following our rhythm, following our game plan here. What is the limit as x approaches 2 from the left of h of x? So again, we're looking for the less than sign here. So this is your function that you want to focus on. So we're going to go with a limit as x approaches 2 from the left of 5 minus x. Once we substitute that 2, we get 3. 5 minus 2 makes 3. All right, let's check out the other side. Limit as x approaches 2 from the right. In this case, the function, the hot function, so to speak, the active function is going to be 3e to the x minus 2. Now, here's a fun one. So you go to substitute that 2, right? Well, 2 minus 2 makes 0, and e raised to the 0 is 1, right? Anything to the 0 is 1. So 3 times 1 makes 3. Oh, winner, winner, chicken dinner. We've got ourselves a match. So I'm thinking here, the limit, the general limit as x approaches 2 of h of x does exist and it's equal to 3. So we haven't ever had success at this point yet. So now what do you do next? So we've got to now, if you go through your checklist there, the second thing that we've got to verify is that h of 2 exists. And this is when you're going to look for, let's see if I can find some more colors here. What looks exciting? Let's try orange maybe. Let's save that orange. So now we look for that equal sign. Oh my gosh, it didn't save. I don't know. I'm goofing that up somehow. All right, so we've got red. So you look for that equal sign right there. Boom. So this is going to be your active function for finding the function's actual height, which, we've already used this function once, so we're pretty confident that it's going to work. So let's say h of 2 is equal to 3e to the 2 minus 2, which makes 3. Again, everything's checking out. So let's verify or conclude that h of x is indeed continuous at x equals 2 because why? Because the general limit is equal to the value h of 2. So this is an x here. So a lot of times this gets confusing. It's going to take practice, but we do definitely want, and we want to be very intentional, we want an x here, but we want a 2 here. So anytime you're using this limit notation here, this is always going to be h of x. When you use the limit, you're never going to put an actual number here until like the next step after that where you try your direct substitution. So it's going to take us a little time to get the hang of it. I do want to try one more. And again, practice makes perfect. I should say good deliberate practice makes perfect. All right, shake and bake. What is the limit as x approaches 1 from the left? Look for your less than sign. This is your function. So we want the limit as x approaches 1 from the left, sine of x times pi. So now I'm going to substitute the 1 for x. And this just becomes the sine of pi. You can always draw your graph. You're going to put your right there, so that's 0. Now, what if I come in and sneak in from the other side? And I want to do the limit as x approaches 1 from the right-hand side. So now, right-hand side, we're looking for the greater than sign. So here's my active function. X approaches 1 from the right, 1 over x minus 2. Now, substitute that 1, and that just comes out to be -1 when you're all done. So we do not have a match. The general limit does not exist. Let's see here. Therefore, the limit as x approaches 1 does not exist, and therefore f of x is not continuous at x equals 1. So, like I said, I think this algebraic approach is more challenging for us, at least for me anyway, than the graphical inspection was. But just stick to that checklist, okay? Let's always do the limit from the left and the limit from the right to try to see if the general limit exists. If we're okay there, then we find the actual height of the function by evaluating, h of 2 or f of 1 or whatever the case, and then just verify, see if they're actually equal to each other. So hope that helps a little bit. Good luck, and fire any questions at us that you might have.